Welcome back. So, in today's video lecture, we will look at the thermodynamic principles of self-assembly. In short, we can also alternatively call it as thermodynamics of micellization. Okay, because we know that at some concentration, surfactant molecules self-assemble to form micelles. The process of forming micelles is nothing but micellization. So we will look at some thermodynamic concepts behind this process of the micellization. So basically, what we will be interested is we will try to find out what is the change in Gibbs free energy, right, and enthalpy of micellization at standard reference state. So basically, we will try to find out what is the change in Gibbs free energy as a function of CMC, and what is the enthalpy, change in enthalpy as a function of CMC. Both are measured at some standard reference state. Okay, let's begin. So we will look at the some of the important concepts before we move on to the thermodynamic aspects. So we will try to understand what is critical micellar concentration. Okay. So first of all, we know that there are two counter acting components. You would say that the surfactant is basically nothing but an amphiphilic compound that we know, which consists of two parts, right? One is nothing but hydrophilic, right, and which is water loving, and the other one is hydrophobic, which is oil loving, right? So these two counterparts. So when you disperse this or dissolve this surfactant into let's say solvent like water or any medium, so because this is hydrophilic is water loving, it would want to maximize its exposure with water molecule. We're talking about aqueous solution here. Now, on the other hand, the hydrophobic part would want to minimize its contact with the water molecule, right? So this is the reason why they have a natural tendency to self-assemble, right? Say whenever we add surfactant, when we prepare an aqueous solution of surfactant, basically surfactant has got a natural tendency, okay, to go to the interface and orient themselves such that the hydrophobic part is kept away from the contact with the water, right? In this way, they minimize the contact of the hydrophobic part with water. So this is the natural tendency, right, for surfactant. Now the question comes, what if we keep adding the surfactant into the aqueous solution? So beyond some concentration, when they arranged in the condensed manner, so because there's not going to be any space available beyond some concentration, right? So whatever we add further, what will happen is they will go on they will go to the bulk, the surfactant will go to the bulk. As soon as they go to the bulk, they combine to form micelles, self-assemble to form micelles in this way. So this is nothing but a micelle. So when they self-assemble in this fashion or self-organize in this fashion, they would try to minimize their exposure or contact with the water molecule, right? So in this way, they can avoid contact with the water molecule. That's why the first, as soon as we add surfactant into the aqueous solution, they will go to the interface, try to minimize the contact. When we add further and further, because there is no further space available, or the surface concentration has reached the saturation level, they'll go to the bulk. But since they are in the bulk, so they will be forced to self-assemble so that they can minimize the exposure with the water molecule. So this is the reason why they self-assemble to form micelles. Now, now there is going to be a transition, and this is going to be an equilibrium process. So what will happen is when I keep adding, when I keep adding the surfactant into the aqueous solution, because they try to go to the interface and remain at the interface, beyond some concentration, the surface concentration will remain the same, because whatever we add further goes into the bulk, right? Whatever we add further is goes into the bulk, and whatever has gone into bulk will try to self-assemble to form micelles, right? So this is the idea. And at equilibrium, the rate at which monomer going to bulk forming micelle and monomer going from bulk to interface will be same, right? Which means that the surface concentration remain intact, okay, even though we add more and more surfactant. But what will happen is there will be micelles will be growing, right? So number of micelles will go up. Okay, so if I have to understand this transition, basically what I can do is I can use this, measure. I can measure the interfacial property like gamma, which is surface tension, as a function of concentration, right? So what will happen? Let's say if I take about example of, let's say, air-water interface, so that is nothing but usually it will be around 72 millinewton per meter. So because you add more concentration, the surface tension goes down, and then it will reach a stage where the surface tension that you measure remains the same, because the surface concentration going to remain same, right? Whatever you add further will not contribute, will not get absorbed at the interface, they will go into the bulk. So this transition, right, the point at which this transition occur, that is monomer to micelles, right? So this point is nothing but CMC, which is CMC is nothing but critical micellar concentration. Okay, so there are other techniques that you can use. Say, for example, you can also measure the properties in bulk, right? So let's say if you want to measure some property in the bulk, let's say some property we measure in the bulk, and as a function of concentration. For example, I am talking about the turbidity. Okay, turbidity is so in this way you can see that there is a change in the slope, because we use the turbidity meter, okay, which measures the NTU units, right? NTU units, and this indicates the measure of cloudiness in the solution and turbidness in the solution, because when they are in the monomer state, right, in the bulk, there will not be solution will not become turbid. But as soon as they form micelles, which is nothing but an aggregate, solution starts to turn turbid, right? From the clear state to turbid state, one can observe this transition from clear state to turbid state using the turbidity meter. So this point, what we measure is nothing but CMC, which is nothing but critical micellar concentration. So no matter which technique you use, the CMC is going to be the same. Say, for example, if I use the conductivity meter, right, in this case also you would see that the CMC is measured at the same point, and because when you use the conductivity meter using the let's say conductivity probe, what will happen is as soon as the surfactant are in monomer state, because it doesn't hinder the ionic movement, you would see that the slope here is the rate at which the conductivity increases is higher than the rate at which the conductivity increases in this case of the domain where micelles are formed, right? So you can say that the transition at which this the point at which this transition occurred from the monomer to micelle is nothing but critical micellar concentration. and these two properties are measured in the bulk, right? Okay, so now we will look at the thermodynamics of micellization. Okay, so as we know that we will the surfactant monomer to micelles, that is aggregate structures, are formed, right? During this process, we can use the reaction approach, right, to represent the scheme. Say, for example, we know the polymerization reaction, right, where monomer is simply converted into polymer, right? Okay, if you have n number of monomer, you will have polymer with n number of segments, right? So this is the simple, reaction approach that we use for polymerization. We can use the similar approach. Let's say you have a surfactant molecule, right? Individual molecule are called monomer. We can use this notation that surfactant molecule, these are nothing but monomer. You can also use this notation to say that these are like polymer analogous to polymer, but these are nothing but micelles, right, or aggregates containing number of monomer molecules or number of individual surfactant molecules, right? Okay, so we can use this representation. We use this equilibrium notation because this process is equilibrium process. At equilibrium, we know that whatever you add further goes into bulk, right? And the rate at which the monomer goes into bulk and monomer from the bulk goes into interface, both are same. So this represents the equilibrium process, right? Okay, so if we simply use this reaction approach, so what is going to be my, so I can represent this as micelles, right? Monomer going from micelles. Okay, so let's start with our criterion of equilibrium. For any equilibrium reaction, we know the criterion of equilibrium is simply nothing but mu i equal to 0. What does it represent is, this mu I is nothing but stoichiometric coefficient, okay, and mu I is nothing but chemical potential, okay. So if I write this in terms of the, in this case, this will be simply nothing but mu1. So you use the stoichiometric convention, negative for reactant, positive for product. So in this way, this will be simply nothing but minus mu1 and mu2, which is nothing but delta mu, which is 0. This is what exactly we represent using this criterion of equilibrium, right? So in this way, if we can start from this step, which is mu I equal to 0. Now we know mu I for mixture. So we are talking about mixture because you have the pure state, that is the water, right? And you have the aqueous solution, that is water plus surfactant, right? So we represent mixture, which is nothing but a binary mixture, here surfactant and water. So this can be denoted as mu I naught plus RT ln Fi bar by Fi naught, right? So this we know, this mu I naught represents the chemical potential measured at same temperature, right, for a standard reference state. So in this case, it can be a pure substance, which is water, right? So we can use this notion, this equation. And what if we substitute this equation into our the previous equation, that is mu I. So here I will simply substitute this equation, which is nothing but RT ln. We know that this Fi bar by Fi naught is nothing but AI. A is activity activity is defined as the ratio of fugacity of a mixture to fugacity at a standard reference state. So this you can replace this as AI, right? So if I decompose this thing into summation I, mu I naught, this is going to be simply summation I mu I naught is simply going to be d mu naught, right? Because for stoichiometry we know that for reactant you use the convention negative, for product you use the convention positive. In that way this will be simply d mu naught, right? So we will have d mu naught which is nothing but minus RT ln AI to the power gamma I. Okay, so we can use this as it is, right? Now we can express this in there are two more steps from here. We can express this into we can explicitly express this activity for micelles and surfactant. So if I explicitly express this for micelles, this will be A micelles, gamma I in this case will be 1 by n, right? Okay. Yeah, right. So then I can say that, okay, plus ln, this will be AS and minus 1, right? Okay. So in this way, I can simply write this as, I can write it as A micelles 1 by n divided by AS. Okay. Yeah. So this I can write as minus RT. So I can again decompose this one. So this will be minus RT ln, 1 by n. Yeah, this will be simply minus RT 1 by n, right? ln A micelles. Okay. Okay. Then you have minus, ln AS. Okay. So this is what we have. So if you say that n is number of monomers, usually very large, right? In that case, we can say that 1 by n will be negligible. Okay. So in that way, we will only get rid of this term. What we will have is simply RT ln AS, right? This is what we will have. Now we know that the activity can be expressed in terms of concentration. Okay. Remember, since we have a ln operator here, so we want to normalize this with respect to some reference state. Usually in textbook, many textbook they use they don't use any reference state here, but if it is not mentioned explicitly, you should understand that it is normalized with 1, right? But in this case, we can use some standard reference state to normalize this one, so that this particular quantity will be dimensionless, right? So in this way, you can say that this is nothing but RT ln C by C naught. So C naught is for the pure water case, right? This is for pure water, and this one is for aqueous solution, right? Which means the binary mixture containing surfactant plus water, right? So now we have the d mu naught, which is nothing but RT ln. We know at equilibrium, we're talking about equilibrium, the concentration that we measured belong to the critical micellar concentration. In that case, you can simply say the concentration that we measure is nothing but the concentration at CMC. So we can retain this as it is, right? So this is nothing but concentration at standard reference state, in this case pure water, right? So d mu naught, we can also represent it as G naught, which is nothing but molar Gibbs free energy. okay, and you can represent this as CMC by C naught, okay. Sometimes you can also use this notation, that is simply instead of molar energy, you will use the Gibbs, right, in this form as well. So in that way, you will have to use multiply with N, right, which means nRT ln, which is nothing but CMC by C naught, right. So what is this one? This one is the change in Gibbs free energy measured at, calculated at standard reference state, which is again function of, CMC, correct? Okay, so that is exactly what we have done so far. Now we will look at the enthalpy of micellization. Okay, we will look at the enthalpy. You will look at the enthalpy of micellization. So now we'll look at the enthalpy of micellization, right? So we will borrow the concept from Helmholtz-Gibbs enthalpy, right? So Helmholtz-Gibbs, right, relation. Right? So this is nothing but let's say G is, if you write G as H minus Ts, then we can say G by T as H by T minus S, right? So if I derive this with respect to temperature, this will be simply minus H by T square, okay? Remember, we have the relationship for, the delta G naught, which is nothing but nRT ln CMC by C naught, right? So we want to use this expression, right? And for that, what we have to modify is both the side you have to use this operator and use this standard reference state notation. So what you can simply write, modify, we can modify this equation simply into dou G naught, right, by T divided by dou T, which is nothing but minus del H naught, right, T square by T square. Okay, so in this way, we can use this expression because this is expressed in terms of change in Gibbs free energy at standard reference state, right? So if I have to use this, then I can say this as NR, right, ln CMC by C naught, okay, which is nothing but minus delta H naught by T square into dt, right? If I integrate on both the side, I will simply have NR ln CMC divided by C naught, which is nothing but delta H naught into 1 by T2 minus 1 by T1. Okay, so I can also express this as ln CMC by C naught as delta H naught NR into 1 by T2 minus 1 by T1. So this is going to be my enthalpy of micellization, right? So here, if we know what is CMC and concentration for a pure reference state, you can calculate what is the change in enthalpy at standard reference state. So that is the idea. Here also you can see that the equation is in the form of function of CMC, right? So that is our objective. So now we have deduced equation for both the case, that is Gibbs free energy and enthalpy. Both are now function of CMC. right? So if you have got a binary mixture, we can actually calculate the change in Gibbs free energy, right, at any pure reference state for the surfactant mixture or solution, right, in this way, right? We'll stop here. We will continue from the next lecture. Thank you.